Okay, I believe we'll get started and let everybody else fill in as they can get into the webinar. Welcome, I'm Tony Olenek from Nascent Technology Corporation, and I'm a member of the AOCS Board of Governors. Thank you for joining us today for our webinar entitled High Throughput Formulation of Sustainable Cosmetic and Consumer Products. This presentation is co-sponsored by the Society of Cosmetic Chemists, the SCC. Today's webinar will be presented by Dr. Amin. We're very proud and honored to have him with us as one of our distinguished professors. Dr. Amin is an associate professor of chemical engineering at Manhattan College, where he currently leads the cosmetic engineering focus area. Prior to joining academia in 2018, Dr. Amin worked in industry for 20 years, working across engineering, R&D, and innovation management areas in global multinationals such as ExxonMobil, Unilever, L'Oreal, Malvern Instruments in Asia, Europe, and in the United States. Professor Amin's experience and expertise is in colloids and complex fluid, rheology, tribology, and advanced characterization of formulation designed for consumers, personal care, home care, and biopharmaceutical products. Professor Amin's research at Manhattan College is focused on formulation design and performance optimization of consumer, cosmetic, and home care products based on novel, sustainable raw materials, including biosurfactants, biopolymers, and novel polymer chemistry, including stimuli responsive or smart polymers. Dr. Amin's research group additionally works on protein stability and rheology control in high concentration biotherapeutic formulations. Many of the research projects are carried out through collaborations with leading global cosmetic and biopharmaceutical companies. Dr. Amin serves on many committees, both nationally and internationally, the Royal Society of Chemists, the Society of Chemical Industry, and has chaired numerous international conferences on complex fluid, soft matter area in Europe and in the US. He currently is section editor for Current Opinion in Colloid and Interface Science Formulations and the Cosmetic section. He owns a he received a PhD in chemical engineering from North Carolina State University and his master's degree from Johns Hopkins University in chemical engineering and a BS in chemical engineering from Rutgers University. Dr. Amin has also carried out a postdoctoral fellowship in soft condensed matter physics group at the University of Freiburg in Switzerland. We are very happy to have him with us. And I would ask us as one or two housekeeping items, if you have questions, please put them in the question box and we will have them answered at the end of the presentation. Again, thank you very much for being with us. And Dr. Amin, I'll leave it over to you.
Thank you so much again, Tony, for that introduction and for the time today to go through this kind of area, which I think is a growing and important area for across the world of formulated products. So not only kind of relevant for cosmetic and consumer products, but I think the concepts that I'm going to talk about are relevant across any industry which uses formulated products, whether it's paints, inks, and coatings, foods, cosmetics, consumer goods, home care, etc. So it's a broad range of industries which I think are working on formulated products, where I think some of the concepts that we're going to talk about is going to be important. So again, thank you for that opportunity, and thank you everyone for joining us today this afternoon here in the US. And if you're joining us from Europe or Asia, it's probably getting towards the evening. So again, thank you for your time later in the day for kind of listening to this aspect of things. So what I'll talk about today, again, as I mentioned, is this area of high throughput formulation design. And what I'm going to go through is maybe like a slightly different than a normal scientific talk, in the sense that I'm going to go through some examples, but my main focus for this talk is kind of looking at where do we need to be in terms of our strategy as we kind of move into kind of the future of formulation design, right? So that's kind of where I'm going to be focusing on, rather than just kind of going into the details of scientific results, because you can all read that in the scientific publications that I'll kind of highlight to you. So that's what I'm going to be focusing on. So if you don't see kind of me going into the depths of mechanistic aspects of things, that's because I want to cover the breadth of the concepts that I want to kind of get across in terms of the strategic direction that I think formulated product industries need to be moving in. And we'll go through that through some examples. Before I go through that, a lot of you might not know where Manhattan College is. We're based in Riverdale, part of New York City. So unfortunately, we are all still kind of almost getting over the kind of the lockdowns and everything else, at least here in New York City. So getting life starting to get back to normal. So hopefully, if you're in the area, I'd kind of encourage you to visit us in Manhattan College. It's a very beautiful campus, especially now in the summertime. So it's a nice place to kind of visit, and I'd be happy to host you and show you around in terms of our facilities. One of the things which Tony already alluded to is that we do have a very specialized program at Manhattan College within the chemical engineering department, where we're focusing on cosmetic and biopharmaceutical engineering. So this is both at the undergraduate and graduate levels, and where one of the things that we wanted to do here was to give kind of build up the domain knowledge for our students in kind of formulations, polymers and surfactants, colloids, all of these domain knowledge that you need in order to enter into the formulated industrial sector, if you will, especially in R&D and product development. So this concentration area is registered with the state of New York, so they actually do get a concentration on their transcript. And in addition to kind of understanding about formulations and other things, we are a chemical engineering department. So in addition to kind of building the basics understanding of colloids and surfactants and polymers and formulation design on specific type of product formats, what we also end up doing is kind of doing specialized courses on scale up and manufacturing of these sort of products. So again, there's lot of nuances, a lot of challenges when you are dealing with complex fluids, which we are all working with every day in the formulated industrial sector. So kind of what are the nuances that you need to understand when you're doing the scale up? That's kind of some of the things that we kind of advance the knowledge for the students. We do a lot of collaborations with global companies, and that gives our students kind of the flavor of how it is to work in industry by they haven't even graduated yet, but they still get the flavor of how it is to work in a fast-paced industrial setting, because we work almost as if we are in an industrial setting. We work at a very fast pace with these companies. We use robotics platforms to kind of formulate, as you'll see here. And that I think is a very good training for the students. So I just wanted to give a little bit of a plug-in in terms of the program that's present at Manhattan College from that perspective. So now let's kind of move into, and you can ask this question. So we've been formulating for a very long time. Why do we need to kind of rethink about how we are formulating? So what's the need? Why do we have this sudden urge of kind of moving towards faster and smarter formulation design? Well, I would say that's basically the market and kind of how things are changing and how things are changing really fast, right? So basically, if you look at, especially if I look at the cosmetic area, for example, you are kind of getting market pressures from multiple directions, right? So basically, there's all these kind of indie brands, right, which are kind of eating into your kind of revenue streams, right? There are this need for customers to have, or end consumers to are asking for increased customization of the products, right? There is a need as you want to distinguish yourselves from your competition and from all these indie brands, you need to have differentiated products on the shelf, right? And that has to be both from a functional perspective, but also from a sensory perspective. So how do you build that into your product and have a kind of a winning product on the shelf, right? How do you do that? And then there's this whole aspect about moving towards naturals and more sustainable products, and this whole area of clean beauty, right? And where it's not only about kind of environmentally green footprint, but also kind of thinking about the ethical sourcing of ingredients, etc. Right? And then there's also shorter product life cycle. So there's a lot of market drivers and pressures which are present right now. I think I just gave an example of the cosmetic industry, but the same sort of examples can be drawn from kind of the consumer area or other formulated product areas, right? Because how do you really start to kind of survive in this environment, especially if you want to start to project ahead 5-10 years into the future, right? Where do you think the world will be in terms of moving towards a smarter formulation design? Because I think that's what is underpins today's kind of discussion, if you will, from that perspective. So as you think about all these challenges that the market is putting on kind of the industry, how do you kind of address those challenges, right? So one way is obviously to try to think about novel materials and approaches to address these challenges, right? So you have to think about, where do I kind of get to more biodegradable, more sustainable ingredients? So you start to look at things like biosurfactants or green surfactants. So people are looking at biosurfactants, bio-based surfactants, all of these things. Biopolymers, again, people are trying to think about, how do I kind of replace traditional petrochemical derived polymers and surfactants, and how do I replace them with things like biosurfactants, bio-based surfactants, or biopolymers? How do I distinguish myself in terms of sensory and functional benefits? Can I bring in things like stimulator responsive polymers? Can I actually make smart materials an integral part of my formulations, and thereby can I actually develop smart formulations, right? I always say that it's not about smart materials, it's about smart formulations, because the formulation as a whole has to be smart. Otherwise, the consumer is not going to be perceptive of any changes that you make, right? So that's very important, right? It's not about, okay, I'm just going to kind of tinker with a material and that's it, and basically I'm going to spend to the nth degree understanding that. If the consumer cannot perceive it, it's no point for me. I mean, I'm a very applied guy. I've worked 20 years in industry, and for me, it's always about what is perceivable, what is actually going to make a difference here. So I think kind of really understanding that aspect about taking what's there in terms of the underlying ingredients, but actually designing the formulation, or as I call it, engineering the formulation to kind of act in a smart way is what is going to make a difference at the end of the day. So that's important. The whole area about the skin microbiome, right? Again, how do you interact with the skin microbiome? How does the product interact with the skin microbiome? Because again, that's your first interface as the product kind of meets the skin, right? For example, or meets the scalp. So how do you engineer those interactions in the between the microbiome and the product, right? So those are considerations you'll have to take. So if you think about this area, you see that it's really blowing up now, right? Because you see that there's so many possibilities there, right? In terms of where you can start to make a difference in your formulations, right? Whether you're looking towards sustainability, or whether you're looking towards novel formulations which are smarter, or you're trying to address microbiome considerations. These are just few examples. But you can now start to see there's multiple suppliers working on each of these aspects of things. And then you, as kind of maybe an end product company, a company which actually does the formulation, you will start to think about, what's the best way I can bring these components together to have the biggest impact on the market. And I want to have that biggest impact on the market in the fastest possible way. And not only in the fastest possible way, I want to do it in terms of having the most differentiated product in the fastest possible way, right? So you have a tall challenge, and there's an area of work in terms of formulation which can seem very daunting. It can seem overwhelming, that how do I actually kind of come to this area and kind of do it in a systematic way. So hopefully what I'm trying to do today is try to give you some of that thinking, to start thinking in this direction, in terms of how do we kind of take all of these developments and start to work in kind of a focused way to get to that end goal, which I just talked about, right? So let's start by talking about maybe just one aspect of things, because in an hour's time I can't focus on everything. But let's talk about, let's say, about sustainability, right? So as one area maybe that you're interested in, and you want to kind of go along with this whole aspect about sustainability, green kind of products, clean beauty, all of these aspects, and you want to address that, and you want your products to be recognized as being part of that initiative, if you will. So if you're talking about sustainability, then let's kind of think a little bit about that, right? Because why, again, similar, right? Because from the market perspective, there are strong market drivers in terms of pushing towards the need for having more sustainable green products, right? Where the consumers actually feel good about the products. They know that they're not having a detrimental effect on the environment, right? So that's critical for them. They feel that they want to be part of that process. So how do you get to that, right? How do you give them what they're wanting, right? So if you are a formulator and you're sitting in one of these industries which makes formulated products, and you see this market demand, you think to yourself, okay, this is great, I need to address this. But then you think it's not that easy a challenge. It's not that easy a challenge, right? This is not that simple to address. It might look simple on paper. Oh, I'm going to just replace everything. I'm going to remove all my synthetic kind of sourced materials. I'm going to replace them with all biodegradable and natural ingredients, and I'm done. Unfortunately, it's not that simple, right? So because remember, you want to have products which are not only sustainable, but they need to have they need to be on par in terms of performance with your traditional products, or maybe even surpass the traditional products in terms of performance, right? So that's important, that's critical, right? So if you think about this whole aspect of things, of how you want to get there, so you think about, okay, I bring in novel sustainable chemistries, novel ingredients, and as I bring in there, it brings to itself a whole set of new challenges. I need stability in my system, right? I can't give an unstable system to the consumer. I need performance, right? I need performance in terms of sensory, if it's a body wash or cleanser, foaming. I need rheology build, so it needs to have the right sort of texture. Lubrication properties for conditioning, right? All of these things, surface lubrication, for example, for home care. All of these are your kind of performance parameters which you want to kind of control and you want to kind of make that optimized. But before you get to that stage, it's about understanding what's going on in terms of the formulation, right? Because as you introduce new ingredients, what are the interactions which are going on there? What are the kind of phase behavior aspects which are going on there? What sort of structures or microstructures are forming in your new formulation? What impact does processing have on it? Because as you'll see, I'll give you some examples. It's not only the formulation which can affect performance parameters. Your processing parameters can equally impact these performance aspects, and you'll see an example of that today. So how do you kind of bring that formulation processing aspect together to give rise to, again, the physicochemical properties, whether it's a deposition or in your interfacial structuring or kind of, again, rheology and texture? How do you get to that kind of physicochemical property which is going to give rise to your optimized performance, right? So this is, I call, knowledge-based optimization. You have to go and iterate through this cycle here. But as you'll understand, it's not trivial, because as you start to introduce more kind of complexity to your formulation, the challenge starts to blow up, right? And that's where kind of a traditional DOE and kind of doesn't get you to the kind of the level of optimization you not only want, but I think you need going into the future. So this is where things like high throughput formulation automation is going to come in, where AI and machine learning is going to come in. And again, I'm going to give you kind of the aspects of where these things could kind of play an important role as you start to think about how are you going to think about formulation as you plan for the next 5 years, for example. So as you think about these things, one of the things to think about is that most of these products, when you think about formulated products, we're dealing with polymers, we're dealing with emulsions, we're dealing with structured surfactant systems. They're complex fluids, right? And the thing is that these complex fluids are kind of ubiquitous, right? They kind of are going into all these products, right? Whether it's a paint, ink, or coating, a kind of a toothpaste, a food product, a biopharmaceutical. They're all formulated products, and they're all kind of complex fluids which have structure and dynamics on multiple length scales and time scales. They self-assemble, they kind of structure at surfaces. They have a plethora of very interesting properties, and it's because of those properties that we get the performance benefits that we want, right? And now we're being challenged to kind of get those same sort of spectacular properties with a whole new set of ingredients. And how do we kind of get to that, right? How do we kind of optimize that aspect of things? So if you just look at some of the product types, you have, again, things like shampoos, conditioners, body washes, cleansers, all are kind of can be the main kind of aspect of there is the surfactant system, right? So the surfactant can self-assemble into multiple different structural formats. If you look at skin creams, lotions, lipsticks, foundations, they're all emulsions. So again, structuring the emulsion, maybe kind of understanding stability in the emulsions, all of these things play a role. And then you're increasing the complexity, because you're usually not going to just go with a surfactant system. You're maybe going to put in a polyelectrolyte in there in order to get deposition effects. You're going to put in film forming polymers. How do those interactions change as I switch from synthetic surfactants and polymers to biosurfactants and biopolymers? How does those interactions change, and how can I re-optimize that scenario? So if you start to see, there is a kind of a slew of papers which have come out over the last 12 to 18 months from my group, all addressing these aspects on emulsions, on structured surfactant systems. How do we make kind of these emulsions which are sustainable? How do we make emulsions which are smart and sustainable? How do we make shampoos and conditioners which are sustainable but still have the right level of performance? I'm going to give you some flavors of that, but I kind of refer you to all those publications over the last 12 to 18 months which have addressed these aspects of things. And I'm going to give you two examples here. Some of it you might have already seen in some of my other talks. So again, apologies if this seems a little bit repetitive from that perspective, but I think it's interesting to kind of think about it. So the first one, we're going to talk about our shampoo or cleanser systems, where we start to kind of replace SLES which is the most common anionic surfactant used in body washes and shampoos, with biosurfactants, and we'll see what happens there. We're going to look at more sustainable formulations with biosurfactant and silk fibroin, and where we kind of move towards a completely sustainable formulation, and we see what happens there. And then I'm going to talk about hair conditioners, where we're looking at a novel sustainable cationic surfactant, and talk about composition effects and processing effects. But underlying all of this, as I said before at the start, I'm maybe not going to go into the details of the mechanistic aspects, but want to give you a flavor of what actually happens when we start to move towards sustainability. What are the challenges which are facing us in terms of formulation? So I want you to think about it from that perspective instead of kind of drilling deep into the mechanistics. You can read about the mechanistics in all the publications, but that's not really what we're here for today. So again, let's talk about formulation design for a sustainable shampoo or body wash or cleanser. It's very similar. It's all surfactant structured system here, and the surfactant plays a very critical role in these formulations, right? And you'll see that in a bit. But these formulations still, even if the surfactant is the key kind of player, if you will, because it has a key role. If you're looking about shampoos or cleansers or body washes, it plays a key role in terms of cleaning or foaming or rheology, right? So it's an important part of the story. But then we additionally have other components in there, right? We have conditioning agents, which might be, again, silicones. We might have, again, kind of polyelectrolytes to help with deposition. We'll have kind of, again, chelating agents, other things. But in these sort of systems, your surfactant plays a critical role, right? Because it's multifunctional, right? So it has the role of kind of actually being able to impact on the rheology. So you don't usually even need any additional thickeners. So if you're, or any rheology modifiers, if you're working with your traditional sodium lauryl ethyl sulfate or cocoa amidopropyl betaine, you know that basically that there is a rheology build with salt, the traditional salt curve as the formulators know it. So you know this is kind of the meat and potatoes, if you will, of a body wash or shampoo. But the surfactants also have a significant role, or the main role, in terms of cleansing efficacy, in terms of foaming. So if you are now going to touch on the main ingredient, which is going to have so much efficacy impacts, it is a big deal, right? Because your whole product is being held together by that performance of the surfactant. So now, as I'm going to now change that, and I'm going to take something else, it's going to have an impact, right? So as I said before, for example, if you look at just one aspect of things, like building up viscosity and structure in a shampoo or a body wash, the system is this very simple anionic sodium lauryl ethyl sulfate and the deuterionic cocoa-amidopropyl betaine. And the betaines in the presence of salts are known to strongly interact with these anionic surfactants to form elongated worm-like micelles. And the betaines are, like when you're at that low pH, although it's deuterionic, it takes on a slightly cationic nature. And that cationic-anionic interaction, it kind of allows you, and then in the presence of salt, allowing more screening of the charges, allows you to build up these long worm-like micelles. And these then kind of give rise to the strong rheological response that you see. So you can kind of, just with the addition of salt, you can go from a system which is almost water-like in viscosity to something which is extremely strong gel, and when you turn it over, it doesn't turn over, for example. It's because it's a very strong gel. And it doesn't end there, because I mean, then if you keep on adding salt, you can lose viscosity. But there's a very interesting kind of aspect of building up viscosity, and those who have formulated with these sort of systems in body washes and shampoos, like certain things can disrupt that rheology build, right? So addition of perfume and perfume molecules and fragrances can disrupt it. Some other additive can disrupt it, and all of a sudden you lose viscosity. And that's because you're disrupting the microstructure, you're disrupting the worm-like system. And that's quite interesting to understand. And we're just kind of starting to kind of understand that as aspect as well. And now we have to switch to biosustainable or to sustainable components. So it's kind of about re-understanding or re-establishing those underlying microstructural insights, if you will. So if we start to kind of look at this system and we say that, okay, what happens when we replace less by a biosurfactant in such a system? What happens to it? So here, in order to look at this, we started to look at glycolipids. We looked at sophrolipids and rhamnolipids. Again, these you must be quite familiar with. These are interesting from the perspective that, from a commercial perspective, they are being kind of scaled up from that perspective. So you'll find kind of, again, from the biosurfactant world. So remember, biosurfactants are more microbially produced surfactants, as opposed to bio-based surfactants, where you can get from polysaccharides and sugars and other things as well. So APGs are more of a bio-based surfactant, whereas these glycolipids are more biosurfactants. That's just kind of semantics in terms of how the nomenclature goes for these sort of things. But the whole aspect is it's about biodegradability, and as you start to switch these with SLES, what happens, right? And for these sort of glycolipids, one of the things is that because it's difficult to kind of isolate very pure forms of these things, it becomes extreme. They're already very expensive, so you don't want to add more expense. So usually you'll see that as you go to commercial sources of sophrolipids and rhamnolipids, or the sources which are scaling up, now you'll see that you get mixtures. So basically you'll get kind of lactonic and acidic forms of sophrolipid. You'll get rhamnolipids with mono and dirhamnolipids from that perspective. So you get usually mixtures from that perspective. And what we wanted to do was to actually work with more commercial type of products, because again, we wanted to kind of get to that insight, right? So again, here you have rhamnolipids and sophrolipids. We source them from sources which are scaling up these biosurfactants. And started to explore what happens when we substitute these things with SLES. And one of the things you see here is that this is a very simple example, right? So that what you see that when we start to kind of introduce a little bit of biosurfactant into an SLES cap B system, what does it do to the viscosity? So if you look here, the red line here is basically just SLES at 16 weight%. When you add cap B to it, because of those favorable electrostatic interactions, you actually build up further viscosity because of elongation of the worm-like micelle. So you get to that green curve over there. But now and that green curve is basically 14% SLES and 2% cap B. Now, if I start to replace that 14% cap B by 2% of rhamnolipid, you see the viscosity drops drastically, right? So it kind of comes down to that blue line here. So you have dropped viscosity considerably, and you can look at it in the sample pictures that the yellowish tinge colors, they're much more liquid-like. And this kind of changeover is happening because you are changing the microstructure of the system. And as I said, I'm not going to go into the onto the details of the study here, but this was just an example of what is happening when I do a very simple substitution, right? But here, what we wanted to do was to challenge ourselves that, okay, how do I rebuild up the formulation, right? So what is kind of the experimental design I need to do in order to explore the variables that are here, right? So basically, this is a ternary system of 3 surfactants, right? Because you might think that why can't I replace SLES completely with biosurfactant? And you can, it won't build up any viscosity, not for this system. But here, what we wanted to do here was that we wanted to slowly replace it and see that can we make it at least a little bit more biodegradable? Can we start to replace that? And one of the things which is important as well, you might think of it from a market perspective, is that if I slowly build up kind of the demand, then that will increase the supply slowly as well, and then eventually we'll get to kind of the economics will be a bit better in terms of pricing. So that was also another rationale here as well. But from the perspective of understanding this, we understood that basically the whole aspect has to do with electrostatic interaction. So right, so and there are charged species in here, right? So there is an anionic SLES, there's a zwitterionic cap B, and there's a rhamnolipid which is kind of fluctuates a little bit like the zwitterionic based on pH, goes from kind of slightly anionic to slightly non-ionic from that perspective. So there are these fluctuations which go on when you start to change the pH. And then so under different pH conditions and different electrolyte conditions and different ratios of these surfactants, you will get different behaviors. You'll get high, low viscosity regions based on what mixture of these formulation variables you're going to play around with. So that's what I wanted to indicate to you here, that you can already see how this experimental design is going to blow up on you, right? That's a big challenge now, that how do I kind of get to that level of optimization when the number of variables that I could explore is so broad, right? So that's a fundamental challenge when you are going to think about optimization, right? So again, I kind of go back to this journal article for you to read about the mechanistic and insights. But what I wanted to show here is this is what we'll need to do. So how do we do it is more of the focus of this discussion today afternoon. But I wanted to give you a flavor. This is what's happening. This is what we need to do. How do we do it? Right, so we'll get into that in a little bit. So that was just about rheology, and you just saw a little bit substitution has a drastic impact on things, right? So it's a big challenge with kind of optimizing pH, ratios of ternary surfactants, electrolyte levels, all, and that's just for the surfactant system. What's happening with the same sort of system? What happens when we on the foaming and cleansing? Because remember, I said surfactants are multifunctional, right? So you're going to impact on both the you're going to impact on the rheology, the viscosity. You're going to impact on the foaming properties. You're going to impact on the cleansing properties, right? So here, for example, we started to look at surface tension, and on this graph on the left, you see that basically we start to replace kind of traditional surfactants with CCB, which is your rhamnolipid. And we start with a pure cap B or a pure SLES, and with a pure SLES cap B, and we start introducing more and more of this rhamnolipid. And you see here what is quite interesting is that especially with the cap B system, the cocoamidopropyl betaine system, you see that you kind of get to a surface tension reduction which is actually lower than either the SLES Cap B system, and is definitely lower than the pure Cap B or pure SLES. But you get good properties when you combine SLES and Cap B. But what we've shown here in this work is that actually can even outperform that by actually introducing now this Cap B system, this CCB or this rhamnolipid into the system, and kind of get to an even better point in terms of optimization of the surface tension or reduction of the surface tension. And we see that I don't kind of go into it here, but this is also in a Journal of Cosmetics, a cosmetic science publication, where we show that we also kind of have a more optimum surface elasticity. So low surface tension, high surface elasticity is kind of a good recipe for good foaming performance, for example, right? So what we did here is that in this optimization exercise, where we're varying all these formulation variables, you kind of see that you can actually start to impact on the foaming performance. So you see the ones with which you have slightly yellowish tinge are the surfactants that are the biosurfactant based systems that we've optimized at those ratios. And you see again here that that the longevity and the quality of the foam, especially the second from the right, is quite different from even the traditional synthetic surfactants. So actually, to that question, we can not only kind of substitute bio-based ingredients, but we can design through formulation optimization. We can design systems which actually outperform our traditional surfactant-based systems. So that's kind of the take-home message for this aspect of things. But you can read more about this again in this Journal of Cosmetic Science publication. But how did we do these two exercises, right? On the rheology and on the foaming, how are we actually approaching this? This is where we kind of start to talk about kind of exploring wide formulation space to optimize performance, right? So automation, where it comes in. And here I collaborate with a Swiss company known as Chemists, who have very kindly provided one of their automation platforms in our lab, which we have found tremendously helpful in terms of optimizing formulations and actually being able to explore this formulation space, right? So for example, here is kind of the ChemSpeed Flex Formax, kind of what it looks like. It doesn't have a very large kind of footprint in terms of the lab space. And what you can see here basically again is that you have these 6 reactors, if you will, where you are, and these are the mixing vessels, where you can control temperature, heating, cooling rates, the extent of shear that you apply in the system, for example, right? And again, the details of these you can always kind of talk to ChemSpeed about. I just wanted to show you here that these automation platforms actually allow you to kind of explore this wider space. So basically all you have to do here is you have to use kind of just calculate as you would in terms of what are the formulation kind of ingredient concentrations that you want, and you fill in the required amounts in the ingredient trays, right? So you have like about 80 ingredient trays where you can put in multiple different ingredients or starting materials or raw materials, and then you have the 6 reactors and you kind of load them up. And pretty much you then have to write the script in terms of what exactly the automation platform needs to do, right? So it needs to transfer a specific amount of the material into the desired reactor, right? It needs to select which reactor, which amount of stuff is going to go into, how much heat is going to, it needs to heat it up to, what rate it needs to stir for how long, and then kind of cleaning procedures, and then you run the script. And that's an example of the script that you write for kind of doing this sort of experiment, right? So you see each step, you can kind of specify exactly what you want it to do, and it's exactly going to do that, and it's going to do it for multiple reactors or mixers, right? So that once you write the script, you can just keep on rerunning the same script over and over again for the same sort of sequences, if you will, in that formulation. And here you can see basically you have SLES and everything else which we have highlighted here, in which we're doing this sort of SLES transfer, right? And here is kind of again a schematic which shows you the 6 reactors. It has these labels, right? You'll see in the yellow 1 and 2 are the raw materials, and we tell what is in those raw materials, right? Is it salt? Is it silicone oil? Is it SLES? What's in those kind of vats? Which it's going to take up, and we tell it already that you're going to take up this amount and put it and dispense it into that reactor, and then carry out all those steps. So again, this is all programmed in through the scripts, right? So here, hopefully, I didn't actually check, I forgot I had a video, but hopefully you can see this video if I play it. Just gives you a little bit of insight in terms of how this takes up the raw materials and then dispenses it into one of these mixers. You'll see it, the needle head kind of dispensing it into it. And then you'll see a little bit of video, I think, of the mixing going on. Yeah, so here you can see the mixing going on now. There's obviously heat being applied as well. It's a heated jacket. So this is just example of one platform. In some companies now, obviously, in order to get high throughput, you can actually put multiple of these stations in parallel and kind of get really high throughput kind of output from that aspect of things. Okay. One of the things which kind of is interesting here is that some of the things which we do manually can end up being quite tedious. I remember I was telling you the importance of pH, right? Because when you have a ternary system like the one I described with SLES, rhamnolipid, and CAP-B, where all of their electrostatic interactions can be tuned by kind of pH conditions, it can be quite tedious to explore those things and kind of see how you're kind of doing pH adjustments. And the other thing is sometimes you'll want that even is to control everything to a very specific pH, right? So how would you do that? I mean, manually you can do it, but it's challenging. But what the ChemSpeed has the capability to do is basically have fully integrated pH measurement built into the platform, right? So it can actually measure, not only measure the pH, but can also control and adjust the pH as well by kind of, again, so it kind of takes kind of your neutralizer, your acidic base, and then basically takes a pH reading, sees what it is, and then if it's not at the set level, it can kind of readjust as well. So that whole exercise becomes much more simpler. The other thing, which is sometimes a quality control parameter, and which you saw here, for example, as we are changing all these ratios and we're changing all these kind of pH levels or electrolyte levels, can we get at least a quick measurement of what it's doing to the viscosity? So again, you can have this fully integrated viscosity measurement tool, which is available on the ChemSpeed, again on the Flex Formax, to actually measure what's going on in terms of viscosity as you are changing these formulation variables as well. So that's another aspect, right? So these can become quite time consuming and challenging, but if you can do all of that in an automated way, life becomes much more simpler, right? And that's what I was saying, as your kind of experimental formulation space really kind of really diverges, you're going to be challenged with kind of getting to that optimum level. So again, automation can really help in that context, right? I mean, I gave you the example of the SLES CAP-B system from both a surface tension and rheology perspective. Let me give you two other examples where we have used, again, this kind of approach to optimize our formulations. This is where we have kind of moved towards, in the previous example, we still had SLES and CAP-B in there. Here, we're trying to create from scratch almost a completely sustainable cleansing formulation or shampoo formulation, right? So here, this was a collaboration with Evolve by Nature, which is a Boston-based company. They also have a cosmetics line known as Silk Therapeutics. One of the things which is, I think, the key aspect of Evolve by Nature and is a proprietary technology of them is this silk, is this kind of activated silk, as they call it. So basically this, so what Silk Therapeutics does, or Evolved by Nature does, is that they take organic and natural silk cocoons, they purify them, they extract the fibroin, the protein, through a specific process, and then they convert into liquid silk protein feedstock, and they can then customize the chemistry further. So one of the things we wanted to do was to understand is that can we optimize a system where we kind of bring in these benefits of a biosurfactants with the benefit of a protein system, which is also sustainable, and bring this in terms of getting some synergistic interaction, which can optimize performance, right? So this is, so you're starting, so you have never brought these two materials together, and now you're going to explore a broad space of different ratios, pHs, electrolyte concentrations, all of these things. And again, this is where automation really helps to kind of to speed up that process. So for example, here, one of the things we wanted to do was to first optimize the surface activity between silk and this capryl glucoside, which is the surfactant that the bio-based surfactant that we were using. And here you see that we looked at kind of SLES, CAP-B, glucoside by itself, the sophrolipid and rhamnolipids we discussed before. And then we saw that, okay, how can we get to a surface tension value now between this mixture of silk and capryl glucoside, which is actually beats all of these guys. So that was a big optimization exercise of playing around with all the different ratios, electrostatic interactions, and then we came up with this magic ratio, if you will, of silk to glucoside, where we optimized and minimized the formulation, minimized the surface tension of the system. Also, I mean, I'm not showing it here, but we also enhanced the surface elasticity of the system, and you can see what it does here in terms of the foaming, right? So here again, the second from the right, the SFCCG sample is the one we have optimized for its surface tension and surface activity. And we compare it with the other things which you were seeing there. So here you can see differences in the foam volume which is being produced, the foam longevity which is being produced, and that's all the result of getting to that sweet spot of that ratio, and that's not trivial, right? Through that optimization exercise to get to that level of optimization where we have kind of achieved this, which a consumer can actually see and benefit from. But that all the work that went into it was all that optimization, which I told you about through that iterative loop, right, from that perspective, and using automation. We did cleansing as well. Sorry, and from that cleansing perspective, what we saw here is that again, we could get a system which was actually pretty decent in terms of getting percentage sebum removal. So kind of good performance on beating performance in terms of foaming, very good performance in terms of cleansing. But the problem was this system was not viscous at all. It was still very low viscosity. So here we had to introduce a biopolymer. We introduced these carrageenans and xanthan gums, and we again optimized that formulation to get the kind of the right rheological profile for getting good sensory benefits, right? So we have to not only get beating foaming performance, like really, which beats everything else, but then also good cleansing, but on top of that, build up good viscosity, and not only viscosity, but the entire rheological profile, which gives rise to kind of a very optimized sensory performance as well. So here we kind of engineered the interactions between the carrageenans and the protein and the biosurfactants. So it's a ternary system, and we optimize that interaction perspective. And again, here you need that sort of high throughput formulation development in order to get to this level of optimization. And this is just for a 3-component mixture, right? But even there's many formulation variables which you can play around with, right? So that's important to kind of understand from that perspective, that we can actually create things which are sustainable, which can kind of are along the lines of clean beauty and all of that, and we can get to that stage with things which are high performance, right? And so these ratios, I don't have it here, but you can look up. We actually Evolved by Nature has filed a patent on all these formulations, and the patent is actually now public domain, so it came out. So it's a patent you'll see with Manhattan College, but it's owned by Evolve by Nature. But they have the patent out, and you can see the breadth of a formulation space that is covered in that patent. So if you look up silk fibroin with carrageenan, or you look up under my name as an inventor, you'll see this this patent. There's also a publication in International Journal of Cosmetic Science which came out on this area. So you can look at both the patent and the publication to understand that aspect of things of this optimization exercise. So the last example I want to give here in terms of the need for automation platforms is primarily to talk a little bit about not only the importance of the formulation space, but also the importance of the processing space, right? And this is work that my student Omalade actually did. She did some excellent work on this sustainable hair conditioners. So I'll kind of present some of the work she's recently done on this area. So again, if you look at conditioners, basically these are these CTAC or BTAC based cationic surfactants with fatty alcohol, cetyl alcohol based systems, where these combinations form these lamellar gels, which are very strongly interconnected lamellar gels. And these interconnected, densely packed lamellar gel structures actually give rise to the rheology of the system, or the texture of the system. You then can have additional conditioning agents like silicones, etc. And one of the important things which is interesting to understand is that this lamellar gel structure, which is actually responsible for your conditioning performance, is not only kind of controlled by formulation aspects, so like the ratio of the fatty alcohol to the cationic surfactant, but it's also impacted quite strongly by the processing conditions. So that's going to be an interesting thing to kind of think about also for these novel sustainable surfactants. So here we kind of are very grateful to Inolex for kind of supplying us with some of their novel sustainable cationic surfactant, the aminosensil, right? So where it combines two functionalities, a protonated amine and fatty ester. And basically, again, you have a biodegradable ester linkage group derived from amino acids, and the lipophilic alkyl tail group derived from vegetable fatty alcohols, right? And this system also similar to your cationic CTAC or BTAC based systems. It builds up a lamellar gel structure, and you can see the cryo-TEM from that sort of a system here. And here what we wanted to do is explore two different things. Similar to the SLES CAP-D system, we wanted to explore the formulation variable effect on performance, but we also wanted to explore the processing effects. So remember those 6 reactors, and I said that basically, obviously, you can choose different kind of formulation variables within each of those reactors, but you could also just explore the effect of processing by having the same formulations, exact same formulations in those 6 vats, but change the processing condition in each of them, right? So basically explore the effect of changing shear rate, right? So you shear at a different shear rate in each of these. So your mixing shear rate is different in each of these vats, right? Or you kind of do the extent of heating or cooling is different in each of these vats. So you could be exploring that, and that's what we did actually in this example. We explored the effect of shearing and how that affected on performance, right? So, but first we explored for this aminosensil, because it's a new surfactant system, in terms of its benefit of just with the formulation aspect of things. So here, very simple, we did wet combing tests. And the higher the wet combing test, the better the performance. And you see we get really great performance with kind of changing the concentration of the aminosensil, right? And we get really high kind of detangling values, if you will, in the wet stage. And that's okay in terms of formulation. That's maybe expected. But as I said, what we wanted to also do here was to look at processing effects, right? So if effect of and we wanted to explore that by changing the processing variables on the automation platform. So here in this case, shear rate. So one of the things which I was saying is that these systems, build up very strong lamellar gel structures which are very strongly connected. They're interconnected, okay? And that interconnection gives rise to yield stress, right? Basically, so which means that basically there's a critical stress which you need to surpass before the system breaks and starts flowing. So if you look at a conditioner system, you'll have to usually give it a little bit of a squeeze before it comes out. It's not like a shampoo where it just flows out as easily, right? So that is the critical stress or yield stress that you have to surpass. So what we did was in each of these 6 reactors, we kind of applied different rates of shear when we were making these formulations. So going from a shear rate of 2000 to 3500. And we wanted to explore what does that shear rate do in terms of affecting this yield stress or this interconnectivity. And we see that it has a very nice kind of relationship between the kind of the shear rate that you use. Like with the higher shear rates, you end up with lower yield stresses, so systems which break apart the structure more easily, right? And when we kind of started to look at that and how that relates with the wet combing force, we saw that that was very interesting, because these differences in the shear rate also created similar differences in the combing force variation, right? So, and that's interesting because I've always said this hypothesis is that, and it's validated here, is that the yield stress is responsible for kind of maintaining the structural integrity of the conditioner as it kind of, as you apply shear and you apply it on your hair and it's breaking down, right? Because the higher the yield stress, the greater the structural integrity of it as it kind of comes onto the hair. So your kind of coating on the hair is better. And as a result, you get rise to better wet combing performance. So by affecting the shear during the making, you affect the interconnectivity. You have, therefore, that interconnectivity affects, obviously, the manifestation of that is the yield stress, and the result of that is kind of maintaining a kind of a more integrated structure on kind of coming onto the surface of the hair. So that's kind of the interesting thing which we could explore by, again, using the automated platform by changing these variables and then doing the evaluation. And we did the same thing for CTAC, and again, it was the same sort of results. I'm not going to go through that, but again, so this is, we're writing this up for publication, so you should see this quite soon. But again, for the CTAC, we see the same level of effect of shear on in terms of both the yield stress and the wet combing performance from that perspective. So that's all and good. So the last couple of minutes, what I wanted to do was talk about the future even further. So as I kind of go in, the automation platform is here, but AI and machine learning is also coming in here now as well. So how do we kind of think about this in an integrated way, right? So examples I just gave you, still, I mean, you saw optimization, but they were still optimizing within a very limited space. Because if you think about the entire formulation space available, it's really broad. And as you increase the number of raw materials, it keeps on increasing, right? The number of kind of variations you can look at can really blow up, right? And that's even with automation and multiple parallelization of automation platforms, it'll give you a good headway into it, but it's still kind of not maybe going to get you to the eventual end goal of complete optimization of all the available space, right? So as you kind of increase kind of the number of raw materials, you're kind of, and you're trying to stabilize, and you're trying to go after multiple parameters. We just talked about a few parameters, but in your formulation, you're going to try to optimize everything. You're going to try to optimize viscosity, stability, some sort of sustainability index, right? And maybe some other parameters as well. This is a big challenge, and you have so many multiple raw materials which you're going to start to change. But now you just saw the example. It's not only it depends on the raw materials, but also depends upon the process parameters, right? So all of these inputs of raw materials and process parameters are going to kind of blow up your kind of experimental space that you're going to be interested in exploring, right? Because the way we do experimental design, even with the kind of the wide exploration that we do in our labs, you're still exploring a small subset of the entire formulation space which is available to you, right? So you can get an indication with, let's say, if you have two raw materials, between raw material 1, raw material 2, which spots are giving which spots. So remember, see the language I'm using, which spots are giving you highish viscosity, which are giving you lower viscosity, and where the target viscosity lies, you don't really know, right, in which combination of these raw materials 1 and 2 it lies. I mean, we do that optimization exercise then, but it's quite challenging from that perspective, right? And the more the raw materials you have, right, the number of experiments that you need in terms of the combination of different ratios of the different raw materials that you can be using can really blow up. A lot of you do have kind of your, I guess, chassis or your kind of backbone simplex formulations that you utilize. But if you are going to rethink complete formulation design, maybe you need to start from scratch to kind of make a completely sustainable formulation, and where you have all these different possible combinations of raw materials, and it blows up, right, as you start to increase the number of these raw materials in terms of the number of variable number of ratios you'll need to explore, right? So it becomes really challenging from that perspective. And if you think about that aspect of things, and you want to start to optimize things, you're going to start to have to think about, okay, how do I bring in things like machine learning or AI into this fold, where I'm already maybe starting to do automation and optimization, like I said, told you before. How does machine learning and AI now fit into this and kind of further help me optimize, right? Because now, as I said, because as I'm increasing the complexity of the system, and as I'm kind of making this more complex, and I'm making more and more adding more raw materials, and I'm adding more output parameters, this things becomes quite challenging. So you start off with basically some training, I would say, training sets where you have some relationship between raw material 1 and raw material 2 and viscosity, and you use that to start to train your kind of machine learning and AI algorithms, and start to refine that as you go and optimize it. And that kind of initial training is people think it's a lot of ratios you need to do, but it's not that many actually. So you can start off with a small number of it really depends on your input, right? So if you have like 2 raw materials, right, your usual kind of and you're wanting to, for example, optimize viscosity, let's say that's an output, you don't have to worry about the output really in terms of the experiment, but you have to think about the kind of the input parameters, right? So if you have 2 input parameters, you'll usually need n plus 1, right? So you'll need about 3 kind of different ratios of raw material 1 and raw material 2, and basically how those 3 ratios affect the viscosity. And even just that can be your first starting point in terms of training the AI and machine learning algorithms. But as it starts to become more and more complex, based on the relationship between viscosity and the raw materials, if your viscosity raw material relationship is more complex, it's not a simple linear relationship, then you're going to have to increase the number of experiments. So that's important to realize. And there again, automation is going to play a role, because you're going to have this broad, and it's usually that the case. You don't have a simple relationship between kind of the raw materials and a output parameter of interest like stability or viscosity. It's usually quite a complex relationship, and that means you need more and more data. And if that means if you need more and more data in order to start off the machine learning algorithm, then you need automation in order to achieve that, right? And where will that get you, right? So basically, if you look at the picture on the left, there's a hidden reality, something which we don't know within that formulation space, where there's a region of very optimized performance. But we don't see that when we are doing partial just spot checking, because even all the stuff that I told you is still not covering this entire formulation space, right? So if you're doing still something like that, you're going to end up with on the right, you see the possible outcome where you have some modeling and some classical DOE. You're still not getting close enough to the hidden reality. But if you get to kind of good modeling, good kind of measurements with automation, you can get to the level of, and then input into the machine learning, you can get to something which looks closer to the reality or to the hidden reality, right? And from there, once you have that kind of mapping, you can then reverse engineer the formulations which will lie in very optimized positions for you, right? And that can not only give you a winner in the market, it can really create patent space for you in terms of identifying those regions within the formulation space which can give rise to that benefit from that perspective. So here again, this is all work which kind of is done by so again, I'm very grateful to Inflows AI and Abdu for kind of giving these kind of insights and to these slides. So again, we collaborate with him quite a lot in this aspect of things. So again, if you have kind of questions more detailed on this exact algorithms and the way of how the machine learning and AI works, you can definitely get in touch with Inflows AI and to get more insights into these aspects of things. But once, so if I want to kind of recap now in terms of getting to this space and final optimization, as we start to move into these novel sustainable ingredient selection, I want to now modify that first flow chart that I showed you when I started the talk, and I give you a further refined flow chart to kind of end this talk, right? So you start your process by selecting these novel sustainable ingredients, right? You do some experimental design and you do some experiments, right? So in terms of trial batches over the formulation space, you do get some physicochemical parameters, right, through rheology, surface tension, tribology, right? And this you can directly start to link that to kind of perceived effects, right, in terms of cleansing, foaming, and other performance benefits. It can also, the physicochemical parameters can also feed into the machine learning, as well as these kind of these perceived benefit effects can also feed into the machine learning, right? So basically you're feeding your AI system with the whole data for predictive analytics, right? So you're giving them also the performance benefit aspects. You're also feeding in the kind of the physicochemical aspects as well to get to very optimized kind of data, and you do very optimized kind of predictive analytics based on that. And you kind of specify targets based on this optimization, and you reverse the kind of reverse engineer your formulations that you need, right? So again, you kind of, what I've done here is re-established that first flow chart I gave you, bringing in both automation here as well as AI and machine learning, because you will need automation in steps 2 and 3. And then you kind of feed all of that in together with your consumer data into the machine learning, optimize it, and get to your optimized products and formulation from that perspective. So I'll kind of end here. Sorry, I went to the way over time here today, but it was a big area to kind of cover, and I wanted to give you the full flavor of that. Specific details on the automation platform can be found with ChemSpeed. Specific details on the machine learning and AI can be found with Inflows AI. And I again thank both of them for the great collaborations that we've been doing with them. This flowchart and the approach is published in a very recent Happy article, and you can read that as well, where we kind of go through this process again from a little bit more details. So again, I'm not going to go through the conclusions. I kind of gave you the conclusions in that last slide, but I think as we look towards the future, we are looking towards a future where we have to think about integrated automation, AI, and machine learning to kind of not only generate faster formulations, but smarter and more optimized formulations. And again, thanks to all my students and ChemSpeed and Inflows AI for all the support they kind of gave us from that perspective. So with that, I'll end here, Tony, and again, apologies for kind of the delay in this, finishing this.
No, it was very well done. And I think if I can ask you one or two questions, I think we still have a few minutes left. Mm-hmm. One of the questions, or a number of questions, have come in that have to do with cleaning in between the systems. How do you make sure there's no contamination and crossover as you put the different sections together? Is there automated cleanup cycles in between, or how do you do it?
Yeah, so you can run water through them and kind of do scraping and things like that. But in terms of the actual reactors, you can actually take them up, you can move them up and then just take them over to the sink and clean it. Our cleaning procedures when we're looking at these 6 reactors takes approximately 15 minutes to clean.
Okay.
So it's pretty simple.
The second question would be, have you investigated interaction of fragrances with fibers, or the influence of CCB and other replacements on fragrance interaction with fibers?
No, I have not yet. Yeah, that's not something we have looked at yet, but it's definitely something quite interesting to explore.
Okay, next one, is it possible to automate stability studies through high throughput formulations?
Yeah, so I think that's this is always a kind of a challenge there in terms of looking at stability and understanding what is a good early stage parameter for stability. So right now, I mean, you know that your stability, if you're looking at stability, you can do accelerated stability studies, right? So again, you kind of either kind of heat them up and store them over a certain period of time. So again, you can obviously formulate there in terms of, again, storage at a certain specific temperature. I don't know if that exists currently within the portfolio of what's available. Maybe it is, but I'm not completely aware of it. You can again ask ChemSpeed if they're aware of that, or what people have done with that sort of an aspect of things in terms of accelerated stability study when you're doing, let's say, at higher temperature. But there are other things which I think are going to come online at some point soon, where basically people are looking at other analytical techniques to look at fast prediction of stability, especially in emulsions. So like right now, you see that there is an integrated platform to do viscosity measurements. So for example, you can get an indication of stability if you're doing like a low shear viscosity measurement and seeing variations of that and how that changes with time. So that's one way to look at it. If you have yield stress, you'll build in stability, so you can look at that aspect of things, which you can do through a rheology platform. But as I said, there's other areas, like for example, in our lab, we have just completed a study. Again, this is something we're writing up using diffusing wave spectroscopy, which is a multiple light scattering technique, and which is very sensitive to changes in the dynamics of emulsion droplets. So what we're looking at there is looking at emulsion droplets diffusion and changes in diffusion profiles and understanding. And what we saw there was that, for example, we could tell early on, very soon after being formulated, which emulsions could be problematic. So that's something we're writing up, which should come out in the next 2-3 months. But I would see in the future, once those early predictor technologies are established, one could integrate them in with automation platforms similar to how the rheology and pH was there. In the future, those sort of platforms could be coming online once they're established. So that's a long way of answering that question.
Well, thank you for that, and we're running out of time, so I appreciate a wonderful presentation. There are some questions about looking at the recording. There is a recording of our presentation today, which will be made available. You'll get an email on it. And the last thing was to thank you again for what you've done, and I'm sure you'll be hearing from a number of the students.
All right. Thank you so much again, Tony, AOCS, and thank you everyone for your time today. I really appreciate it.
Have a good day. We'll look forward to the next one with you.
All right. Thanks. Take care. Bye.